Hello, this is the next video on a playlist that I'm calling Correlation. And here we're going to look at partial correlation. And we're going to develop and prove a formula that takes the partial correlation, say partial correlation of x and y, given x, or controlling for z, x, y, controlling for z, but it expresses it in terms of zero order correlations between the three variables of interest. Now this formula is often given as the definition of partial correlation, but my note is, to me, this absolutely has no intuition behind this formula, for me at least. And I'm going to point you to part 1 for a general intuition of what partial correlation is. And so when you see this formula for partial correlation, you'll at least have a basic understanding of what this is. So it's a correlation between x and y while controlling for z. And so let's prove this formula, and we'll give a little background first. So first what we do is regress y or x onto z. And I'm going to use a centered model. And I have a playlist called Centering and Scaling in my Generalized Linear Models regression playlist if you want more detail on that. But we're going to use the centered model. And the same way for y. When we regress y onto z, we're going to use the centered model like this. So then we look at the residuals. So that's e. So we take their epsilon. We take everything and subtract it over, and that's what we get here. So this is the residual. And we have the residual for y. Now, the partial correlation is actually the zero order correlation between these two residuals. That's what this represents. But of course, we're going to prove that it can also be derived in that fashion. So first of all, let's find an expression for beta 1 and gamma 1. First, beta 1. So we want to minimize this squared error, this squared residual. And we do that by this. So we take what the residual is, plug it in, we get this. Now let's note that it's the expected value of something squared, right? So that's the same as the variance of that, not squared, and then plus the mean of this quantity squared. I always think of it as, if you subtract that to the other side, it's the variance of x is equal to the expected value of x squared minus the mean squared. So that's this formula, but in a different way. So this is it. So now let's look at the variance of this. So the variance of x, which is this piece, constants don't play a part, so it goes away. And then the variance of this, so the mean is a constant, so it goes away. So the variance of this, the beta 1 comes out squared, and it's the variance of z. Then it's minus, because that term is minus, 2 times beta 1 times the covariance between x and z. Now this over here, remember it's quantity squared. So when we take the expected value, we get expected value of x, and then minus beta naught, it's a constant, and then minus beta 1 z minus z bar. So this goes to 0, so we're left with this. Now let's call this function q of beta 1 and beta 0 and beta 1. It's a function of these parameters, which we want to, when we minimize this, we're going to minimize it using beta 0 and beta 1. So let's take the partial derivative of q with respect to beta 1, and so there's no, beta 0. So there's no beta zeros, it's only here. So you take the 2 out front, and then you take that minus 1, and then times the derivative of beta 1. So actually there should be a minus 1 here. Set it equal to 0. But then when you take that to the other side, it goes away. Divided by 2 goes away. Then we're left with this equals 0, which implies beta 0 is equal to the mean. And if you looked at that video I have, finding the least squares estimate of the beta parameters, you would have instantly known that that is the mean of our x's because we're centering. Now, we take the partial with respect to beta 1. That's constant, goes away. Here the 2 comes out and the variance, and then subtract the 1. Here we get minus the, and then the covariance. This is constant. Set it to 0. Divide by 2. Add that over, divide by that. We get beta 1 is the covariance of x and z divided by the variance of z. Now we could do the same thing for gamma of 1, and we would get this. The covariance of y and z divided by the variance of z. Now we're going to use shorthand notation. This is going to be the covariance between y and z, which is what this is. And this is going to be the covariance between z and z, which is actually the variance. So we're also going to shorthand notation this beta 1. So now let's prove the formula. So the partial correlation between x and y controlling for z is this. It's the correlation between these two residuals, which is the covariance divided by the product of the standard deviation. That's by definition what a zero order correlation is. And I would look at parts 1 and 2 for more detail on that. So let's expand this. So let's plug in what the residual for x is. It was this, the residual for y, and the same way down here. Those go in. Now to take the covariance of the top, we take the covariance of x and y. The constant doesn't play a part, so then it's minus. This constant comes out front, covariance between x and z. That's a constant, doesn't play a part. Constant, so then it's beta, z, beta 1, so z and y. That's what this is, and then z and z, so it's this. Well, I probably could have put the covariance between z and z, but that's the variance. And, the product of those is what this is. Now we do the same thing here. So the variance of x, that's a constant, doesn't play a part. The squared comes out, or the beta 1 comes out squared, variance of z, and then there's going to be a covariance, minus 2 beta 1 covariance. Same way over here. Now, what I want to do is write this in the little shorthand notation. So this is the covariance between x and y. Now beta 1, or gamma 1 was this, and then the covariance between x and z. Beta was this, covariance between z and beta 1, gamma 1, variance. We do the same way with the bottom. So that's squared, variance of z, minus 2, da 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 da. Now we start simplifying. If you look at this here, so this variance cancels with this, and then we have the product divided, 1 minus 1 plus, so they actually cancel each other out, and we're left with this. Right, so that's this. Now here, this piece cancels with one of those, and so we have this minus 2 of the same thing, so we're left with just minus 1 of them. Same way here, minus 1 of them, the variance of y, variance of x. Now this next step, what I want to do is factor out a square root of the variance of x in this one, and factor out a variance of y from this square root. And then since we're in the denominator, we can put them, under each of those, and that's what we do here. So it leaves a 1, but since we factored it out, we have to divide by it. The same way here, that's what this piece is. Well, this is the covariance divided by the product of the standard deviations. That's correlation, or zero order correlation between x and y. This is the zero order correlation between x and z. Zero order correlation between y and z. And then this is the correlation between x and z squared, minus 1. Same way here, correlation between y and z. Well, that's what we wanted to prove, right? The partial correlation between x and y given z can be expressed in terms of zero order correlations. And we're done, and that's the proof. Well, I hope you enjoyed this. I sure did. please like the video and subscribe so you don't miss the next one. Thanks. Bye.